Hi, we are Group 12.
My name is Fen Jiang.
My name is Medina Sikano.
My name is Min Xiaoxi.
My name is Yinglu.
Let us introduce our project, which is called the Smart Nose of the Fridge.
In our days, the food safety is a crucial factor for the customers due to the enhancement of living standards. Stale food might lead to economic loss of discarding product or furthermore, food poisoning. Therefore, the price is not important any more than freshness and use-by date during the purchasing. There are a lot of traditional methods of identifying the freshness of the food, such as physical detection, chemical detection, microbial appraisal method. However, this approach had various shortcomings such as long experiment period and strict environment requirements. In order to solve this problem, our group proposed a low-cost and portable electronic nose that can be used in food markets for identifying the spoiled meat and the products containing carbohydrates. Meat is mainly composed of water, protein, and fat, and the carbohydrate can be found in a wide range of foods such as fruit, vegetables, and grain food. Enzymes and bacteria will decompose protein into ammonia, hydrosulfide, and ethanol, and decompose carbohydrates into alkyl ketone and carboxylic acid. Detecting the concentration of the gases released by food is one way to speculate the food quality with electronic sensors.
Here is our hardware. The sensors we use are these three. This one is ammonia sensor, and this one is alcohol sensor, and this one is temperature and humidity sensor. These two sensors are used to detect the freshness of the food in the fridge, and the temperature and humidity sensor is used to define the speed of spoilage. One thing to notice is that the alcohol sensor and ammonia sensor are analog, so we also use ADC to convert analog to digital. The data is read by a Python script on Raspberry Pi, and then is stored in a CSV file locally on Raspberry Pi. Then we use a Node-RED flow to send the data out to the cloud.
The important thing of our system is that it is designed not for one fridge but for thousands of fridges. So each document in the database includes an attribution of fridge ID. Fridge IDs themselves are classified by different types according to their sizes, producers, etc. The basic work in the Node-RED operates as the following. The IBM IOT platform accepts the data from the Raspberry Pi. Then I add timestamp and poisoning index node, where the data is extracted from the IBM IoT platform every 5 seconds. Here, according to the humidity and temperature values, it found the respective poisoning index. After that, the sensor data goes directly to the cloud and database, which I have already set up. So basically, it is our input flow.
For data analysis, we wrote a Python script to extract real-time data from cloud automatically, and the Python script will keep the connection alive so that any change in the database will update the lists in Python. The sampling period in the demo is 5 seconds for the convenience of test. In practice, we think 1 minute period is frequent enough. As said before, our system is not designed for just one fridge, so the purpose of the data analysis script is to find the data from lots of other fridges of the same type, then using the data to optimize the relationship between gas concentration and time. We call it the intrinsic relationship. We assume that the fridges of the same type follow the same intrinsic relationship. The unit of gas concentration should be ppm, which stands for parts per million. But in our project, we chose to use output voltage of sensors as the unit. We will discuss the trade-off in the report. Every time the Python program accepts a document from database, Before starting analysis, it first checks if the data in the past 20 minutes are normal. Here, normal means there is no unexpected fluctuation in temperature, ammonia, and alcohol concentration. If normal, then start the self-learning algorithm to learn the intrinsic relationship between gas concentration and time. To start the algorithm, we need the initial condition, and in our case, it's the data we measured. In the two figures, y-axis is the gas concentration, and x-axis is the time. The blue dots are the measured value in 5 days. It can be seen that it has a linear relationship, so we set the green line, which is got by least square linear regression method, as the initial condition. However, the result is got from only one fridge, and the linear approximation is not very accurate. The intrinsic curve could be arbitrary, so we split the time axis to 60 time slots, 2 hours for each one. The slope of each slot could be updated by the newly measured data independently. Every useful measured gas concentration is corresponding to one time slot, and the calculated slope will contribute 1% to the updated slope. Besides, the slope of the curve is also proportional to the instantaneous food poisoning index. Then the intrinsic curve is used to do predictions. First, let's show the door opening alarm, which means in the past 2 minutes, the temperature keeps increasing. Okay. Yes. Now you can see send door opening warning to node red. And here a message comes. Well, let's check the functionality of alcohol sensor. This is one. If we put the alcohol sensor close to it, the third column is the alcohol sensor reading. We can find that it's increasing, and in the script we can find it's sending the notification to node red. In node red, the alarm comes out, and at the same time I got a message. Now let's show the prediction. The prediction in this demo is done every 2 minutes. You can see it's sent to the node red, and at the same time send a message to my cell phone, and there is also a website. This website shows the gas concentration over the 24 hours. You can
in the output flow, all the documents will be checked and the latest entry will be searched. As we have found a document with information, it goes to the switch. A decision switch node allows to compare the values and send it to the flow one of two ways depending on that values. Here in our case, if the data type is 1, it will cause the alarm, which happens whenever there is an abnormal environment. For example, if the temperature is increased by the 2 degrees in the past 2 minutes, it will mean that the door is open. There are another kinds of alarms, such as the food is about to spoil or food is already spoiled, etc. If the data type is 2, it will cause the prediction of the food quality. It happens if there is no any threat to the poisoning food, and the food quality prediction is sent 1 or 2 times per day for reminding the status of the food. But if the food is going to be poisoned or already poisoned, it will send an alarm every hour. After that, the relative message will send to the payload or to the mobile phone.
To verify the functionality of our self-learning algorithm, we also did the big data analysis. Because of the difficulty of finding suitable open source database, we created the data samples and did the simulation with Python. In this simulation, we assume the temperature and the humidity are not changing, and the data samples follow a linear intrinsic curve and vary along the gas concentration axis following Gaussian distribution. First, we set fridge numbers to 10. In these two diagrams, the blue line, the blue line is the intrinsic line, and the red curve is the data from one fridge. We can also see the curve fluctuates a lot. In the real case, it may also happen because of bacterial environment or measurement errors. The green line is the prediction line, calculated from 10 fridge samples. We can find that the deviation from intrinsic curve is quite large, so let's try 200 fridges. Now we can see it's the lines overlap. Let's zoom in. Now the prediction line, and it's almost perfect. The algorithm also works if the intrinsic curve is not linear. For example, with exponential from the two figures, we can find our algorithm also works for non-linear intrinsic curve. In our group, I'm in charge of connecting the hardware, writing codes to let Raspberry Pi reading data from sensors, and then sending them to the Bluemix. I also wrote the codes for data analysis, prediction, and big data simulation.
In this project, I was responsible for receiving data from the Raspberry Pi, connecting all the nodes in the node thread, and adding food poisoning index and timestamp, and sending the notifications to the cell phone.
In this project, I focus on design the web page which will upload the data on the website and on your mobile terminal, and I also focus on collecting the data and analyze.
In this group project, I am mainly responsible for data collection and data integration process, and I also participated in some hardware design and web server design. And besides, I also do some data analytics based on the least linear regression from Python.